Hi everyone, so in this video I'm going to talk about a new like searching algorithm, which is basically jump search. In the previous videos I talked about three searching algorithms, which is basically linear search, binary search and order agnostic binary search. So in this whole video is about jump search, and the next video I will talk about interpolation search and other searching algorithms. So let's start with the jump search. So jump search is basically a simple sorting, like a searching algorithm. Sorry, simple searching algorithm is not that difficult, and its time complexity is like much better than the like linear search, but not that great than binary search. Okay, so let's start with the jump search. First of all, I'll like explain it, then we code it, and then before code it, I will explain the time complexity of it. So let's start with it. So jump search. So jump search. As the name already tells you what jump search, like you can already take an idea what jump search can do, what jump search will do. It will jump. It will jump like some step to get to the desired element, right? Like in the linear search, what we'll do, what we are doing, and in linear search, suppose 1, 2, 3, 5, 4. 1, 2, 3, 4, 5, 4, yeah, and we are searching for element. Suppose we're searching for element 5, so we will like compare it with the every single element, every single linearly, and if a match is found, we will just return it index, return its index, right? So this is the case about this is the case about linear search. This is the case about linear search, right? This is the case about linear search. We're doing this one, and we're getting our result. We're comparing with every element in the array. But what happens with jump search? We're not taking like one step, but we're taking some big step depending on the size of the array. If the size of the array is very big, we'll take some big step. If the size of the array is small, then we'll take small step depending on the size of the array. So what we'll do? The main thing is what you have to do. The main idea. Let's explain the main idea of the jump search. Okay. So basically the jump search is basically a variant of the binary search. The condition of the jump search to use jump search is the array should be already short. Okay. Uh, Either in ascending order or in the descending order. In both the cases, it will change some of the conditions. If it is ascending order, it will have some other condition. If it is descending order, it will have some other condition. But other than that, it will be same. In this video, I will be talking about ascending order, anything order, like how to do the jump search in ascending order list. Okay, and in the descending order, you can do it by yourself, of course. Okay, so let's talk about that. So suppose you have a list. Suppose you have a list like 2, 3, 4, 5, and 6. Suppose you have a list. Okay, let's go to the second page. I think not great to do that there. So it will be 2, 3, 4, 5, 6. This is the a list of elements. Okay. Now what happens in the jump search? We take some steps. Suppose we are doing here. Suppose there is 7, 8, and 9. Okay. Suppose we are doing here. Since here are how many elements? 8 elements. Suppose we are taking two steps. Not taking one step. We are taking two steps. Suppose we are taking two steps. So step we are taking is 2, right? Two steps we are taking. So this is the zeroth index. This is the 1, 2, 3, 4, 5, 6, and 7. Okay, and the target value is, target value is, suppose target value is, we're targeting for 6. Suppose, okay, now we're targeting for 6. Suppose we're starting with 0. So we're talking about, is this element is okay? Is this element is comparing the target? So it said no, it is not. So now it will go to the next step, like step this current index plus 2. So we'll go to this one. We'll go to this one. So is it okay? I'll say no. Or basically it will not directly compare it. What will check if the second element, this one element, is greater than 6. Is it greater than 6? No, it is not greater than 6. Now I'll say, is 4 greater than 6? This is how the jump search works. Is 4 greater than 6? We'll say no, 4 is not greater than 6. Now we'll check if 6 is greater than 6. It will say no, 6 is not greater than 6, it is equal to. Now it will again take one step and it will say if 8 is greater than 6, it will say yes, 8 is greater than 6. Now I'll stop there. Now I'll stop there, and what it'll do, it will do a linear search in this like sublist. It will do a linear search in this sublist. So if it do a linear search, so it give a new list 6, 7, 8, and it will, if it do a linear search from this one, so it will be 0th index one, like not 0th index actually, but if it is something another list, then it will be from 0th index. So and do a linear search and check for we have a target of 6, so let's check, is it equal to 6? Yeah, it is equal to. So it will return its index, it will return its index, return. Okay, that's how the jump search works. It will take some specific specific step depending on the size of the array. I will talk about how to calculate the step. Okay, depending on the size of the array, and it will go to the step and will check if that particular current element is greater than the 6. If it does, then it will take to the its previous step, and from that to the current step it will just like from it stop there na? So it will go to the previous step, and from there to here, from there to here, it will just do a linear search here, do a linear search, do a linear search, linear search. Okay, do a linear search. So that's how your element is found. Okay, that's how it will be. This is the simple logic of the the jump search. Now I hope you understand it. It is not that difficult, but the thing is how to calculate the step. How to calculate the step. Okay, so to calculate the step, suppose we have n elements, norm of elements we have is suppose m, right? Sorry, n, n, and norm of elements is n, and we are suppose taking taking some steps. So suppose we have this list. Suppose we have the previous one is 2, 3, 4, 5, 6, 7, 8, 9. Yeah, and we're taking here two steps. 2, 8, 2, sorry, uh, 2, 3, 4, 5, 6, 7, 8, and 9, right? And here in this case we have a 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 8 elements, 8 elements, and taking two steps, and steps equal to step equals 2. That means 8 upon 2 will have four iterations. That means this one, then this one, then after that it will go this one, and after that it will go this one. Yeah, 4. Yeah, we will have 4 iterations, 4 steps if we divide it. That means the norm of steps is dependent on and upon the size of the array, upon the step number, how much step we are taking at a time, right? That means if we're taking the step, suppose m or s is the step, suppose s is the step, size of step is equal to, suppose we're taking s. That means norm of steps, norm of iteration in the array will be n upon s, like this one. And after that what we are doing, we are just making this one, what we are making, we are just like taking we are also doing linear search in this step, this is also s step, this one, this is also step s, like 8 minus 6 is 2, it is equal to the step only, so it is also step, that means s only plus s. Okay, it is also s only. So what we have to do, suppose we want the whole thing to be done in a minimum steps, how much minimum step it can be, the minimum step can be 0. We want the whole thing to be calculated in a 0 steps, right? That means this norm of steps, norm of iteration, actually norm should be equal to 0, right? Should be equal to 0. Yeah, you can say that. That means norm of steps, like norm of iteration, we want it is minimum step, norm of iteration, for minimum step, for minimum step, for minimum step is equal to 0. That means you can say it is n upon s plus s equal to 0. Okay, and if we multiply it above s square upon s equal to 0, that means okay. And now what I'm making it here, is uh, we are just eliminating the thing. Suppose we are taking the minus, okay? So n equal to suppose s square. Now, we are just eliminating the minus. Although how much minimum step we can do from here? How much minimum step? So n upon s, minimum step is actually 1. So s minus s square. Yeah. So minimum steps. I don't know how many minimum steps can get. Uh, minimum steps. Is it n? Is it can be n? And s? No, it can't be. Can't be. If it is equal to n, so s square will be ns minus s square. S will be taken common, and it will be n minus s. So that will be tedious actually. Yeah, that will be tedious. So we can just assume that we just like eliminate the minus part, and just you have to take s equal to, it will be root n. So it would be great. It would be great, or you can just refer some other books to know how this like jump search step we can count it. But this is the logic actually. And upon s, and we're also doing linear search in a jump search for the step like s step, so it will be plus s, and that's how it works, that's how it works. Yeah, that's how it works. So that's the case. So that's why we need root of n steps. We need root of n steps. For this one, we're taking 2, right? Why taking 2? Because 1, 2, 3, 4, 5, 6, 7, 7, 8. So and root of 8 is approximately equal to 2. Like not like approximately is greater than 2. Greater than 2. And if we take in integer value, it is greater than 2. So that means it will give some integer value, some sort of integer value here, so floating point value. So now if it is converted to integer, it will give 2, right? That's why it is 2. If it be 9 with 9 elements, that will be root of 9 will be 3. So then in that case step will be equal to 3, right? That is step will be 3. So in this case is 8, so root of 1 will be 8. Root of 8 will be equal to 2. That's the integer value, only the integer part. Okay, so that's the jump search. That's how we calculate the steps. Now let's see how let's see what's the time complexity of any space complexity. Let's jump into that. So time complexity, the time complexity. So if it's the time complexity, in this case like 2, 3, 4, 5, 6, 7, 8, 9. In this case, we're taking step 2, right? And we compare to this, and this one. Then we have done 4 iterations. We have done uh, uh, typically 4 iterations. Step 2, 4 iterations. Okay, that is okay. That's great. 1, 2, 3, 4. Yeah, 4 iterations. So we have done 4 iterations. That means this number of steps and upon n, right? So for 4 iterations. So whatever the number, 1, 2, 3, 4, 5, 6, 7, 8. So 8 divided by 2 we have done, right? Plus what we're doing, also we're taking 2. Also we're taking 2 here. So here it is 2. 2, so it will be 8 plus 4 divided by 2, it will be 12. 12 divided by 2 will be 6. Right? It will be 6. So now assume we have n steps. Now assume we have n steps. Now assume we have a n steps. Steps like n numbers, n elements you can say. Elements equal to n. Okay, and that means step is equal to root of n. What do we got there? That root of n. That means now if we calculate this, now if we get upon to develop elements divided by this one plus the step, the linear search what we're doing here, right? Linear search we're doing here, it will take two steps. Like two iterations will be like 0 1 2 like that much step, or again 2 plus 1 step, three iterations will do. Okay, so that is the case. So or you can say 2 minus 1, like 2 plus 1 you can say. You can say here is 2 plus 1, it will be 3, 3 will be, it will be 6, right? It will be 6 and 3 and 6 and will be 8 plus 6 is 14, 14 divided by 2 is 7. This there. Okay, so here the linear search, in this case linear search uh, linear search is equal to root of n plus 1. So so the total number of steps, you can say total steps equal to n upon root of n plus root of n plus 1, right? So if we divide it, so we'll get root of n plus root of n plus 1, and we'll do 2 root of n plus 1 total steps. That means if we remove the constants from the total steps, what is the time complexity we get? That means time complexity is equal to big of root of n. Okay, and if we talk about the space complexity, since we're not taking any extra spaces, any extra auxiliary spaces, that's why space complexity is big of 1. This is constant space complexity. Now how it is efficient? If we're talking about efficient, let's see. In case of linear search, since we're making every comparison in the list, linear search, the time complexity is n, big of n. And in the jump search, it is root of n, of root of n. And in the binary search, it is of log, right? So actually linear search is less efficient than the jump search, and jump search is less efficient than binary search. Okay, uh, in some cases, but in some other cases where I know the number of comparisons matter, sometimes jump search is better than the binary search. Sometimes, not all the time. Sometimes jump search is better than the binary search, but in the most cases, jump search is less efficient than the binary search. Okay, that's the whole explanation of the jump search. Now let's get in the code of it. It is very easy. It's very straightforward. If you didn't understand it, just replay it and see the video if you want. Now let's go to the code part. Yeah, let's go to the CodaGo folder. You're doing searching, then go to the searching folder, and let's create RAPL here. That is the programming language of Java, and here the Java, and name is jump search. Let's talk about now the jump search. So let's code it. Let's first of all make a function, then jump search. Yeah, let's first of all make a function, and jump search. Yeah, static int, which is the index will return after the search completed. So jump search, it will take an array. It will take an array of integers and a target value. Okay, and a target value. So first of all, what we will check? It will just first of all calculate the step it will required. So in step equal to, we'll do the match square root function, square root, taking out the square. So the length of the array, here dot length, we're passing the length of the array, and the whatever value we'll get will like explicitly typecast this to the integer value. So it will be uh, int. I'm passing a int. So to only take the integer part of the like floated number, the return number, the square root number. Okay. So with the step value, now let's take an iterative variable, which is basically I, and I equal to 0. And first of all, we'll check a condition before going to the other steps. Whatever target we have, is it out of the range? Is it out of the range? In that case, we'll return -1. That means what I'm talking about. Let's go to it. Yeah, here. Suppose we need a target of suppose 7. Target of 7 in this list. Okay, this list. So what happens here? Target of 7, that means target of 7 doesn't lie between 2 and 6. So we have to check if the target is lies between 2 and 6. If it doesn't, then what will return -1? That we have to check. If it doesn't fall under this range. Okay, because since it is a sorted array, so if we check only the last element and the first element and the last element, then it is okay. Then we don't bother about any smallest value, largest value. Don't bother about that. Just we have to check for the first element and the last element, because it is already sorted array. Remember that it is a variant of the like binary search. So what I can do, we just have to check a condition. If the error of 0, like the first element, if it is like it is greater and the target is smaller, that means here we have, suppose we have a value 0 here, suppose we have a target of 0 here, and 0 is here, right? So that means this target is smaller than the first element, if it does. And also, or the last element here, dot length -1, and the last element we have is equal to it's basically smaller and the target is greater, and the smaller target is greater, then what will return? Will return -1, because the like the element, the target is not in the list. Not in the list, yeah, because 7 is greater than the last element. Okay, so now what we'll do, we'll check, we'll now iterate through the step. What step we get here, will iterate through the step. So first of all, it will check a condition. If I is less than arr dot length, I should not be should not exceed the length of the array, otherwise it will get an array out of bound exception, right? And now what have to check? If arr of I value is greater than, is basically whatever the I value is basically greater than the target. If it does that, then only but by the way, we're talking about here the ascending order list. Okay, ascending order list. While error I dot length and error of I is greater than target. Okay, so now here incrementing the step, and if this condition gets now false, so it will take out of the loop. Okay. Now again, we make a start like variable where we like taking the start of the sub list, where we are doing the linear search. The start of the sub list where we are doing the linear search. Like in this case, this one. In this case, this one. The linear search. Here we are doing the linear search, right? So the sub list, where we are starting. So in the normal case, if ARR basically if ARR is equal to 0, that means it is in the element is in the first thing only. It didn't go to the next one. In that case, what to do? Start is also equal to 0. We will not do step -1. We will not do the previous step, because there is no in previous indexes. Else, what to do? Start will be equal to I minus step. Like we'll go to the previous step. That means if it stops here, it will go to the previous step, right? That means I, this is the current index, minus the previous step, that means the previous element. Okay, I minus step. Now we'll do a linear search, doing a linear search in the sublist of the array, and here we're doing 4 int k equal to start, and or we just taking the start index only, start, and here we're doing I, or here we can start is less than uh, or equal to uh, start is less than or equal to I only, the current one, and start is plus plus. Now we'll check for the element. If ARR of start is equal to the target, then return the start. Okay, then the start, doing making it, and at the end just return -1 if it can't find. But although it is already taken care of here, but like yeah, since we have to return something at the last, so we are returning -1. Okay, so that's the whole code. Let's put the value in the function. So let's make an array. When is this equal to new end, and here we are now things like 2, 3, 4, 5, 6, 7, 8, 9. It's supposed to up to 8. We are taking, okay, 9. So now let's take a target element, and it is supposed we're taking 4. Okay, and let's do system dot out dot print ln, and let's make jump search here, and it would be we're passing the ARR and the target also. Okay, and let's see what will happen. uh, it should not give an error, I guess. Let's see. Okay, it's giving me -1. Why is giving -1? Target is greater. Yeah, it is actually okay, but why is giving me -1? uh, if it is equal to, it is also equal to, yeah, it is like equal to them, right? So do not need to do that. Less than ARR dot length, we have dot length, and start, and I equal to 0. Well, I think I have done something wrong here. Start plus plus, I am in a step, I is less than or equal to I, current one, I, y is equal to 0, increased. So start equal to 0, and there will be start equal to I minus step, minus step, and our incrementing start plus plus, start equal to target. Okay, let's do some debugging here and get, let's print the step. Okay, print the step, here doing step, step, and doing step. Yeah, so let's get the step of it. Usually 2, I guess. 1, 2, 3, 4, 5, 6. Okay, it should be out. Yeah, it should be out. I'm doing wrong. I'm getting it. This 2 step is 2. The current element ARR dot 0, it should be greater than the target. The target is smaller than that, and ARR dot length -1, 2, 3, 4, 5, 6, 7, 8, 9. ARR dot length -1, it should be less than, target is greater than that, so it will be -1. And I plus equal to step, so ARR of I, the present element, what we have now. If it is implement, if it is lesser than the target, I guess. Okay, if it is lesser than target, then it will continue to do. If it is greater, if it done greater, then it will stop. Yeah, yeah, that's the that's the mistake. Sorry for that. That is the mistake. Now it will, yeah, let's skip 2. It will be 0 1 2 for the elements 2. If we give it pass it 7, then it should give me 0 1 2 3 4 5. It should give me 5, I guess. Let's see. Mm, let's give me 5. This is the last element 9. Then check for that. uh, yes, it is taking time because of this my PC. I'll upgrade it soon. Yeah, it's giving 7. 0 1 2 3 4 5 6 7. Yeah, it's giving 7 is right. Now it gives some element which is not in the list. Now let's see, it can give -1 or not. -1 or not. Yeah, it's giving -1. And let's take 2, the first element. Let's see, is it can encounter this kind of this part or not. Yeah, it can encounter it. So that's the whole code of the jump search actually. So if you like the video, then share with your friends. Share in Twitter, LinkedIn. If you're learning in public, then take in screenshot of this video and share it on social media with the hashtag learning with Ronak. That'd be great. So that's it for today. See you in the next video. Bye bye.